Chapter 1: Magnetism. Now, people have for thousands of years known about the magnetic properties of certain types of naturally occurring materials such as lodestone, which is a form of iron called magnetite, and have long utilized this phenomenon for navigation in the form of a compass. And that is because magnets, when suspended freely, settle facing the north-south direction. In this chapter, we want to understand more about magnets and magnetism. So we begin with properties of magnets, and let's start with magnetic poles. When a magnet is placed in a pool of iron nails, the nails get attracted and cling onto the magnet. It is noticed that a lot of nails cling at the ends of the bar magnet, indicating that the attraction force is strongest here. These ends of a magnet are called its poles. One end is the North Pole and the other is the South Pole. Directional property. A bar magnet is suspended freely on a stand using a thread and allowed to come to rest. It is observed that the magnet aligns itself in the north-south direction. We bring the south pole of another magnet near the south pole of the freely suspended magnet. The south pole of the suspended magnet moves away. This is repulsion. When a north pole of another magnet is brought close to that of the suspended magnet, repulsion occurs. This means that like poles of magnets repel each other. How about unlike poles? We bring a north pole near the south pole of the suspended magnet. The poles attract each other. When a south pole is brought near the north pole of the suspended magnet, the poles attract each other as well. This means unlike poles attract each other. This is the basic law of magnetism. Unlike poles attract, like poles repel one another. Next, we talk about magnetic and non-magnetic materials. Now, we are all probably aware of certain things that are attracted by magnets. Examples are iron nails, screws, spoons, belt buckles, and so on. Other materials are not attracted by a magnet. Clothes, wooden doors, and wooden tables are not attracted by magnets. Or more specifically, wood, fabric, and plastics do not get attracted to a magnet. You will notice that these materials are non-metals. You wouldn't find any non-metallic object attracted by a magnet. So non-metals are non-magnetic materials. Non-magnetic means if you bring a magnet close, it will not stick to it. If non-metals do not get attracted by a magnet, does that mean all metals do? No. Some metals get attracted while some don't. The most common metal that gets attracted by a magnet is iron. Apart from iron, nickel, cobalt, and steel also get attracted by a magnet. But if you bring a magnet close to copper or aluminium, they will not get attracted. However, copper is attracted by very powerful magnets, but for common small magnets, no attraction takes place. So we can say that the only metals that get attracted to magnets are iron, nickel, cobalt, and steel. These materials are called magnetic materials. And materials that are strongly attracted to a magnet are called ferromagnetic materials. Iron, nickel, and cobalt are ferromagnetic materials. Next, magnetic field patterns. Previously, we said that there is an invisible magnetic field surrounding a magnet. And if you place any magnetic material in this field, it will be pulled towards the magnet. We can visualize this field by performing an experiment. We place a bar magnet on a cardboard. Sprinkle some iron filings on a paper, place it above the magnet, and tap the paper gently. The iron filings arrange themselves in patterns as shown here. These patterns indicate the magnetic field of the magnet. Because of this, we see that the iron filings arrange themselves in a specific pattern. This pattern also tells us a lot about the strength of the magnetic field. We see that more iron filings are gathered at the two poles of the bar magnet. This means that the field is stronger as you move closer to the poles. The field is weaker at the center. The field patterns differ depending on the shape of the magnet. Here is the field pattern for a horseshoe magnet. Again, we see that more iron filings are gathered at the poles. A magnetic field is represented graphically by lines of force. Mapping magnetic lines of force. Now, we fix a sheet of paper on a drawing board. Place a bar magnet on the sheet of paper and trace its boundary. Place a compass at the North Pole. The compass needle comes to rest in a particular direction. Mark the other end of the needle as shown here. Move the compass such that its south pole is where the North Pole was and mark the new position of its North Pole. Repeat this until you reach the other end of the magnet. Join the points with a smooth curved line. The curved line represents a magnetic field of force. Place the compass at different points near the North Pole and map the lines of force. Now let's see patterns due to two bar magnets placed with opposite poles facing each other. We place a paper sprinkled with iron filings above the two magnets and tap the paper gently. The iron filings distribute in a pattern like this one. This can also be represented diagrammatically. Next is patterns due to two magnets placed with like poles facing each other. Again, we place a paper with iron filings sprinkled over it above the two magnets. The iron filings distribute in this pattern, and we can also represent this pattern diagrammatically. In general, the magnetic field lines are close and continuous curves. Outside the magnet, the lines are directed from the North Pole of the magnet towards the South Pole, whereas within the magnet, they are directed in the exact reverse direction. The lines of force repel each other and they never intersect. And so in summary, magnets have a north and south pole. Around these poles are magnetic fields of force that extend out in all directions. These invisible magnetic lines of force leave the North Pole of the magnet, loop around, and enter the South Pole. The lines are more dense near the poles where the magnetic field is strongest. As you move away from the poles, the lines space out due to diminishing magnetic force. Two magnets will repel each other if like poles are facing each other. As you move like ends of two magnets near each other, they will be repelled. Notice how the lines bend as they impinge on the lines of the opposing magnet. If unlike poles are facing each other, the forces will attract one another. As you move the magnets close to each other, the lines of force join and condense, increasing the force of attraction. When unlike poles are lined up end to end, their combined forces create a unified magnetic field and behave as a single magnet. Next, the Earth's magnetic field. So, we have seen that a freely suspended magnet oscillates for some time and then comes to rest in the direction of the geographic north-south. One end points to the geographic north, called the north-seeking pole, or simply the north pole of the magnet, and the other points towards the geographic south, called the south-seeking, or simply the south pole of the magnet. And this is because the Earth behaves like a huge bar magnet, with its magnetic south pole located near its geographic north pole, and its magnetic north pole located near its geographic south pole. And because like poles repel while unlike poles attract each other, the north pole of the magnet is attracted to the Earth's magnetic south pole, which is towards the geographic north pole, and vice versa. The geographic poles marks the Earth's axis of rotation, but the magnetic force exists because of the way atoms are distributed in the Earth's iron core. The magnetic poles actually change their position slightly over thousands of years as materials in the core change position. There is so much magnetized material in the Earth's core such that the magnetic field generated is absolutely immense, stretching out into space. Next is the domain theory. Now, consider a bar magnet with its two opposite poles. When we place compasses at the ends, we can tell the polarity, south and north. When we break it into two and we place our compasses back, it tells us that we have basically created two magnets with two opposite poles. And we can continue breaking the magnets into smaller and smaller pieces, and we will end up creating smaller and smaller magnets. This means there must be magnets within magnets that are causing this magnetism. In a magnetic material like iron, there are small areas called domains, and each of these domains is like a little magnet with a north and a south pole. The domains are randomly arranged and their magnetic effect cancel each other out. So there's no overall magnetism. Such a material becomes magnetized when the tiny magnets point in one direction. For instance, when a magnet is brought close to this material, the magnetic field strength increases and all the domains point in one direction and the material is saturated. In other words, it is magnetized as much as it could. Next, magnetization of magnetic materials. Now, magnetization is the process of making a magnet from a magnetic material. The magnetism may be permanent or temporary. The methods of magnetization include single touch method, double touch method, and electrical method. First, single touch method. Place a soft iron piece AB to be magnetized over a table. Take a bar magnet and place one of its poles on the soft iron piece as shown here. Stroke the iron piece with the bar magnet. When the magnet reaches B, lift it and place it back to the position A and repeat the process several times. The upper side of the soft iron gets magnetized. Now turn the iron piece upside down and magnetize this side in the same manner. The point A will get the same polarity as the pole of the magnet touching it. When this piece is brought near some iron nails, it attracts them, indicating that indeed it is magnetized. Next, double touch method. Place a steel bar to be magnetized on 2 bar magnets as shown here. Now place opposite poles of 2 strong magnets at the middle of the steel bar as shown here. Move the magnets towards the opposite ends of the steel bar, keeping the magnets inclined. On reaching the opposite end, lift the magnets and place them back to their respective original position. Repeat the process over several times. The polarities at the ends of the bar are opposite to those of the ends of the magnets used. When the bar is brought close to some iron nails, it attracts them, indicating that it is a magnet indeed. Next, the electrical method. The bar to be magnetized is wrapped around a long coil of insulated copper wire, which is connected to a source of direct current as shown here. When the circuit is closed, a strong direct current passes through the coil and the bar becomes a magnet. The polarity of the bar depends on the direction of the current. If the bar is viewed from one end and the current is seen to be flowing in a clockwise direction, that end will attain south polarity. If the current appears to be flowing in anti-clockwise direction, that end attains north polarity. If it is a steel bar, it becomes a permanent magnet. If it is a soft iron bar, it becomes a strong magnet and is called an electromagnet. It is a temporary magnet which loses the magnetism as soon as the current flow is stopped. Finally, demagnetization. Demagnetization is the process of removing the magnetic property of a magnet. The magnetic property of a material can be partially or totally destroyed by rough handling, heating, induction, or electrical method. Hammering, dropping, and rough handling of the magnet can demagnetize it. A magnet loses its magnetism if it is heated above a certain temperature called its Curie point. The Curie point of iron is 770 degrees Celsius and that of steel is 880 degrees Celsius. That of nickel is 358 degrees Celsius and that of cobalt is 1121 degrees Celsius. If 2 magnets are placed side by side with similar poles together, each induces opposite polarity in the other. As a result, the magnets lose their magnetism. To avoid this self-demagnetization, the magnets are placed in pairs side by side with their unlike poles together as shown here. Finally, the electrical method. The bar to be demagnetized is placed inside a long coil of insulated copper wire in the east-west direction. The wire is connected to a source of alternating current. The circuit is closed and the current slowly reduced to 0. The magnet loses its magnetism as alternating current changes direction continuously. This changing of direction of the current disturbs the alignment of the magnetic domains, resulting in demagnetization.